All right, let's go ahead and take a look and see what was going on with your motor speed control today. The transfer function that we used was theta m of s over VA of s is equal to k over s tau s plus 1. And you can convert that into the time domain as tau times theta m double dot plus theta m dot is equal to k VA. And we had a control law that was VA equals Kp theta c dot minus theta m dot. I want to just go ahead and look at this differential equation, and I want to solve it. And instead of doing things by hand, I'm going to actually use Matlab, so I'll show you a little bit how to do that. We can use the dsolve command. Okay, so we're going to use the dsolve command to solve for the differential equation that we've generated there on that piece of paper. And the way we can do that is we literally type in dsolve, and then we enter the differential equation as a string. So it's tau times d2, so that means the second derivative of th, which is theta, plus dth, which is the derivative of theta, equals k times v. And v here is just a constant. And so we're saying a constant voltage of some value v. And then I need to specify the initial conditions to solve this. I'm setting them equal to 0. And we hit enter, and bam, there's our solution. So the solution is k times tv minus k tau v plus k tau times v divided by the exponential of t divided by tau, or times the exponential of minus t over tau. So if we use, I can go ahead and just transfer that over here so we can write that down. And so I would then say, all right, well, theta m of t is equal to kt times v minus k tau v plus k tau v times e to the minus t over tau. And what I can do is look at the limit on theta m of t as t goes to infinity. That's obviously equal to infinity. And then I can also look at the limit on theta m dot of t, and as t goes to infinity. And that's just going to be what? Well, I'll take a derivative here, I get kv. Take a derivative there, I get 0. Take a derivative here, I get the tau's cancel out. But this exponential goes away as t goes to infinity. So all I'm left is that. I get k times v. This is essentially open loop, all right, without any gain kp. I could certainly add a gain kp, which you guys did in class. So we see that the commanded speed, the final speed, goes to some value that is proportional to the applied voltage. Okay, that's good. What about if we add feedback? So if we add feedback to the system, we're now essentially substituting in this control law into that differential equation, and we end up with tau theta m double dot plus theta m dot is equal to k p times theta c dot minus theta m dot. And I can multiply things out in here and collect terms, and I end up with tau theta m double dot plus 1 plus kp times theta m dot is equal to kp theta c dot. Now I can go back into Matlab and try to solve this. This is now the closed loop ODE, or differential equations, which represent the system. And fundamentally what we're doing is we've got this system over here, and we're closing the loop around it. So as a block diagram, I have theta m double dot going into an integrator. That comes out, I get theta m dot. I feed that back around through, again, 1 over tau. So tau. Go ahead and add that back to there. And then I have VA there. I've got to feed that through again k, and then add that into the comparator, and I need a minus sign right there. What you guys did in class today was to then close the loop all the way around here, get a comparator going, take theta c dot, and then feed that through the gain, kp. So this is the control, block diagram that you should have ended up with running MATLAB, and most of you got there. And so notice that this differential equation represents this block diagram. So I'm going to go ahead and solve this now with MATLAB, but before I do that, since I'm actually really not interested in theta m, I'm going to make the substitution that omega m is equal to theta m dot, and omega c is equal to theta c dot. Make this substitution, I end up with tau times omega m dot plus 1 plus k kp omega m is equal to k kp omega c. So I'm going to go ahead and solve this first order differential equation in MATLAB. And to do that, I just have to go back and I can use the desolve command. And I just really have to modify what I've got. So I'm going to use desolve. I've got tau times dw, where that's omega, plus 1 plus k times kp times w is equal to k times kp times wc. And now I have to specify the initial conditions on w, and we'll just say that's 0. And we go ahead, run it, we get that solution. And so if I carry that over onto this sheet of paper here, I've got, what do I have? Let's see, I've got to arrange things so I can do this. I end up with a solution for omega m is equal to, what do we have here? Oh, by the way, there's some, if this is hard to read, we can say simple answer, and it tries to simplify it, and then we say pretty answer, and it does that. Okay, so that's a little easier to interpret. And so what is it? Well, it's going to be k p w c all times, well, all divided by, I should say, k p plus 1, and then that's all times this exponential minus 1. So I've got e to the minus t times k kp plus 1 all over tau minus 1. All right, now if we go ahead and look at the limit on this, all right, this is what we're now interested in. What is the limit on omega m as t goes to infinity? So there's my pen, sorry. The limit of omega m as t goes to infinity. Well, notice this term here is going to go off to 0. And I think I dropped the minus sign, didn't I? Yeah, there's a minus sign out front there. Converting from Matlab to, regular math can be a little weird sometimes. So I needed a minus sign there. So I have this negative term times that negative 1, so I just get k kp omega c over k kp plus 1. Well, omega c is the commanded value, so for us that was 1. And so that means that as the t goes to infinity, the speed goes to k kp over k kp plus 1, and that does not equal 1, which is what we wanted. So notice that indeed you find what is true, what you observed in the exercise, but as kp gets larger, this final value gets closer and closer to 1, but it's never going to be exactly 1 because of this little number 1 down there. So in the exercise, we used values of k was equal to 2, tau was equal to 0.1, and kp was equal to 1. And that gets you 2 times 1 over 2 times 1 plus 1, which is just 2/3. And so most everybody agreed that 0.667 was about right. Well, there's your 2/3. So there's really nothing we can do about this. What you should notice is that as Kp gets bigger, the system responds faster, meaning instead of going, like that, it goes like this, and it gets faster and faster, and it gets closer and closer to getting out to the final value, but it never quite gets there. So what do we do about this? Well, tomorrow we're going to look at a way to get around this, and what we're going to implement is what we call, this, by the way, is called proportional control. All right, so this control law of VA equals Kp theta C dot minus theta M dot is proportional control. Right? The voltage applied is proportional, hence Kp, proportional to the error. We can use what we call PI control, where this stands for proportional, and this stands for integral. So this is proportional integral control, and we're going to work on this tomorrow in class.